In today's class, we basically looked at a system of two equations in two unknowns, the unknowns being x and y. And it's two linear equations in two unknowns. So that a linear equation, of course, is one that can be put into the form y equals mx plus b. And we can generalize the idea of linearity to higher dimensions, to equations involving x, y, z, three variables or more. But right now we're just dealing with two. Everything we do with two variables extends fairly easily to three or more variables, except of course the graphing. We can't do that with more than three variables, and it's much easier with two than it is with three. Okay, well anyhow, so here's our equation, 2x plus 3y equals 8, and another equation, 4x minus 2y equals 0. Both of these equations are linear, meaning they contain only constant numbers like 8 and 0, or x, the variable x or the variable y with some number in front of it. Okay, so these are linear equations. They're simultaneous, meaning that we're trying to solve these two linear equations to find a value of x and y that satisfies both equations. Now, I asked everybody to sketch me a graph of two linear equations. Okay, and everybody sketched a graph of this nature where the two lines crossed. In some cases the two lines didn't actually cross, but they weren't parallel, so we knew that they would eventually cross. That's the case where the two equations are what we call independent. Now there are two equations where the equations are not, or two situations where the equations are not independent, and they give rise to graphs where the two graphs, where the graphs of the two equations are parallel. So we see two parallel lines here, and I've got a dotted line here that's indicated to be perpendicular to both, so that we know these lines are parallel. This is a case that we call inconsistent. These equations are inconsistent. There is no value of x or y that satisfies both equations. Any value of x and y that satisfies the equation represented by this line corresponds to a point on this line and won't be on this line, and vice versa. Any point on this line is not on this line, so none of the solutions of the equation this line represents will be solutions to the other equation. Now there's another case, and I just drew this as one line. This is a case where not only are the lines parallel, but they overlap. Okay, so that they're the same line. They're essentially the same equation. They might not look the same, but they are the same equation. This is a case that we call degenerate, where the two lines match, the two equations are actually different forms of the same equation. And then we have an infinite number of solutions, because any point on this line will correspond to a solution. Okay, well, we talked about methods of solving this equation. The first method somebody mentioned was substitution. And substitution is a great method. Substitution is pretty much necessary if you don't have linear equations. But in the case of linear equations, you don't need substitution, and we don't use it in linear algebra. So what we're going to do is we're going to use the process of elimination. And I'll talk in a minute about how we use elimination to simplify this system and obtain a solution.